All right, here goes. We're going to start 9-2 today. Um, we're going to look at graphs of polar equations, which is just sort of a continuation of what we did yesterday. Obviously, I'm not here. I'm actually closing on my house today, and so um, tomorrow I'll be a homeowner. Isn't that exciting? Um, Thursday we'll do a little more on graphing polar equations. There's more kinds, and then Friday we'll start de Moivre's theorem, which is something that we're going to spend a fair amount of time on. Okay, so just some FYIs. If you missed the quiz on Friday, or no, not Friday, last Wednesday, I guess it was a week ago, um, make sure you're doing that during Win A if you haven't taken care of it tomorrow, because I will not be here for Win B when I have a meeting. So, to kind of do what we're doing today, we need to start talking about some algebra skills, and one of the things that I want to uh, recover is completing the square. You're going to see it a fair bit today and on Thursday, and so we just kind of need to cover it again. So here I have a quadratic that's in standard form, and I want to complete the square and create something that's in vertex form like this. So the way that I do that is I split this b term in half, which would be 2.5, and then I need to square that number. So negative 5 over 2 squared is 25 fourths, or 6.25. And so what I need to add to both sides is 5.25, because that creates that 6.25 between this term and this term. So I get x squared minus 5x plus 6.25 on this side, and then I still have this y equals, or sorry, y plus 2.5, 5.25 equals. All right. So now the thing is, this whole thing can be rewritten as x minus 2.5 squared. And then I just need to subtract off the 5.25. So I get y equals x minus 2.5 squared minus 5.25. So this thing right here is equivalent to this thing right here. And this process of adding something to get to this number, where you take your b and divide by 2 and then square it, that's completing the square. So I just wanted to do an example of that because we're going to see it in the next couple days. So anyway, in terms of converting between polar and rectangular coordinates, we have those three equations that are on the screen. And then in terms of just strategies, there are sort of three ideas that we can implement here to get one equation to look like the other form. So the big thing that I want to identify is it's sometimes helpful to square both sides, but it's also sometimes helpful to multiply both sides by r or by something else clever. And so some of this just takes some experimentation, and you're probably going to get a little bit frustrated at times because figuring out what the right strategy is often the hard part of this. So I'm going to give you one example of this. I mean, we'll do multiple examples, but this is the first one. And the one that I want to do this time is I want to multiply both sides by r. Because if I do that, I'll get r squared on this side. And then on this side, I get 4r sine theta. And if I think back to what I have learned in the last couple of days, I know that if I have an r sine theta, I can rewrite that as a y. So I still have 4y on this side. And then this r squared is x squared plus y squared. And so I'm getting to the point of being happy about this equation, but I think I'm not quite done yet. And so what I'm going to do is I'm going to try to get it to look like a form of an equation that we've seen in our lifetimes before. This is like what I have written right now is officially in rectangular coordinates. So I could like circle that and say that's good enough. But what I don't know is what the graph of this thing looks like. And so I'm going to do a little manipulation to see if I can figure out what that looks like. So I get x squared plus y squared minus 4y, and then equals 0. And actually what I'm going to do is I'm going to complete the square here. And so what I need to do is I need to say, okay, well, negative 4 over 2 squared is what I want to be right here. And so negative 4 over 2 is negative 2, squared is 4, so I'm going to add 4 to both sides. And now I get x squared plus y minus 2 squared equals 4. And actually, we haven't done this at all this year yet, but in Algebra 2 we learned that this is a circle with center 0, 2, and radius 2, because this is your radius squared. We will spend more time on this in the next few days, identifying when it's appropriate to complete the square, figuring out when things are circles, when things are other shapes. But I just wanted to show this example. So I'm going to sketch the graph. I know that the center is at 0, 2. So that's right here. And then the radius is 2. So I got this, 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 and this. And then I'll see if I can get my shape tool going. So I can draw a circle. Should look something like that. So the book has some sort of summary, they call them theorems, for like when you have circles and when you have different other shapes. And so this is sort of the summary that I just screenshotted and put into the slides. You can see this in the book too. But if you see equations that are in this form, you can expect to find circles when you do the conversions. So by the way, the rectangular form of a circle is x minus h squared plus y minus k squared equals r squared. So center is the point hk, and the radius is r. And then the thing that I want to do next is I want to just say, like, sometimes it doesn't really even make sense to try to convert because there isn't a clear way to make that happen. If you start manipulating this equation, and I encourage you to kind of pause the video and think about, okay, what could I do to convert this without doing what I'm suggesting here? But you're going to find that this is going to be quite difficult because you can't really ever get rid of r's, or you can't really ever get rid of thetas, and so they just don't really work very well together. So what I'm going to suggest here is that sometimes the inevitable thing here is that you just have to plug in some values and see what you get out. So we're going to do that. Let's just think, okay, real quick, I just want to review. Honestly, use your unit circle because these angles are special angles that are on the unit circle. And so it's going to be easier if you just grab that unit circle and look at your y values, because sine of theta is your y values. So negative pi over 2 is over here, right? That angle. And so if I look at negative pi over 2, I need to figure out what the value here is. So I'm going to do 1 minus the sine of pi over 2, negative pi over 2. And the sine of negative pi over 2 is negative 1. So I'm going to do 1 minus negative 1. And I get 2. So if I go over to that angle, then I'm going to count out 2 and put a dot there. And I'm going to kind of proceed along that strategy for the rest of this, but I'm going to try to go not super slowly here. Okay, the sine of pi over 3, negative pi over 3 is root 3 over 2. So negative root 3 over 2. So I'm going to do 1 minus root 3 over 2, 1 minus negative root 3 over 2, or 1 plus root 3 over 2. All right. Sine of pi over 6, negative pi over 6 is negative 1/2. And so I'm going to do 1 plus 1/2. And then you kind of follow this around. The sine of 0 is 0, so I'm going to do 1. So that means that I have a spot there. The sign of pi over 6 is 1/2, so I'm going to do 1 minus 1/2. So that's 1/2, and that's right here. And remember that I'm graphing all these points r theta, where the r is it's actually the output, right? And the input is the theta. So I go find the angle, and then I draw out the radius from the point 0, 0. Okay. The sine of pi over 4 is root 2 over 2, so I'm doing 1 minus root 2 over 2, which is in here somewhere. And then pi over 3, the sine is root 3 over 2, so 1 minus root 3 over 2. So that's right here. And then the sine of pi over 2 is 1, so I'm going to do 1 minus 1. 1 minus 1 is 0, all right? So then I need to kind of follow this around. I'm going to just pause the video so you don't have to watch me struggle through all of this, but it'll look like this. So I've got those points in there, and then I'm going to just kind of draw the shape, which looks like that. And so this graph is the final graph of a polar function, polar equation. And this graph is called a cardioid because, heart, the word cardiac refers to hearts. So cardiac arrest is a heart attack. And so a cardioid is a graph that looks like a heart. So you'll see that cardioids have this form for equations. You'll just have to do a little bit of experimenting, but generally, if you see something like this, a lot of the time you'll see that this a value is distributed through here. So if you have a 1 plus or a 1 minus, or like a 3 minus cosine, 3 cosine of theta, that's also a cardioid. So the a is just like a scale factor. So the bigger the a, the further away from 0. Anyway, that's the deal. A cardioid will always pass through the pole, and when it says the pole, that just means the origin. So that's the point 0, 0 in rectangular. They just call it the pole because it refers to polar coordinates as that's the reference point. So that's enough talking. You have a book assignment, so either hopefully you grabbed your book to bring to class today. If not, you can use the online version. I'll also grab a couple books to just put out in case anybody needs them. So I hope you have a great day. I will see you on Thursday. I am going to check your homework then. So experiment, try to figure out how to solve and rewrite into rectangular, and then also do a little bit of graphing and just kind of experiment with that a little bit. All right, see you Thursday. Thanks.